Hello all, welcome to the next lecture of network analysis and synthesis. We are discussing the network synthesis part. So till now we have covered what is network synthesis. The input for network synthesis is a network function. So we have seen what is a network function and what is a condition for performing network synthesis. We found out that any function cannot be synthesized. Okay, so it can be synthesized only if it becomes a positive real function. So what is a positive real function? What are the conditions for calling it as a positive real function? Okay, and how to test it with an example we have seen in the previous lectures. So in this lecture, let us go into the actual synthesis. Okay, so the philosophy of the synthesis or the mechanism by which we can synthesize. Yeah. So generally, we are discussing the synthesis of the passive components. Okay, so in passive components refer to resistors, inductors and capacitors, so RLC components, right? So by using these components we can construct the circuits which has only resistors, only inductors, okay, or only capacitors. Okay, or we can go with a combination like RL, RC or LC or RLC combination. All these are the possibilities. Okay, right. In in the network synthesis, when we are doing the network synthesis, right, there are two approaches for synthesizing. One is, okay, based on the properties of the network function, if it is satisfying certain conditions, okay, then it is reflecting to some standard circuits. Okay, so we can based on if it satisfies certain conditions or certain properties. Okay, based on the verification, right, after verifying what are those, we can decide what is the type of the network function. And then because there is every possibility that there is a regular arrangement. When we say standard means regular arrangement of components. Okay, so for example, let us say we have RL, RC or LC circuits. Okay, where R and L are connected in a regular manner like this: resistor, okay, inductor, resistor, inductor, or resistor, inductor. So right, the first step of synthesizing, okay, the first approach of synthesis is based on these standard forms. Okay, so there is every possibility that because right, in most of the circuits that we use or most of the applications that we use have standard way of connecting the resistors and capacitors and inductors, isn't it? Okay, so therefore we can exploit that inherent mechanism and do the synthesis. Okay, so basically in this mechanism, right, we have the structure. Okay, we have a standard structure. Okay, that is a standard way of interconnecting the components, and we find out what components are present and what are their values. Okay, that is one, right? So this is one approach where we are using the standard form of synthesis. Okay, the other approach is whenever the circuit is not having any particular properties or any particular nature, standard nature. Okay, we can say that let's say I have a circuit like this. There are two resistors, okay, one capacitor, one right, okay, random interconnection of resistors and capacitors. So in this case, right, the network function reflecting this kind of circuit will not have any special properties in it. Okay, so we can do this. It is also possible to synthesize them. Okay, it's not that we cannot synthesize them, we can also synthesize them. Okay, but that will be a more general approach. All right, where we have to go for the extraction right from knowing the structure of the circuit and all. Okay, so these are the two approaches. One is looking at the properties of the network function. Looking at the network function itself, we are deciding whether the network function is in some standard form or not. If it is in standard form, we can use the standard approach for synthesizing, where we have some techniques like Foster form and Coyer form, which gives us a standard structure of the for the circuit, right? And they have given the formulas for calculating the component values. This kind of synthesis is very easy. Okay, if at all, if we don't have any regular properties or structure in the circuit, then the network function that is reflecting it will also do not satisfy any of the properties. Okay, it is more general in nature. In that case, the synthesis will be a little complicated. Okay, and we will use the general approach, the basic right, removal of poles, removal of infinite zeros. Okay, all that concept. Okay, so we will discuss both the approaches, right? So first we will discuss the standard approach because it is a simple one, right? And it gives us the right, it will make us path easy. Okay, because directly doing the tough thing is right, not suggestible. So we'll learn the easy things first and then we'll go to the right, tougher ones later. Okay, so the first form of approach or the first method of approach for the synthesis is using the standard approach. Okay, using the standard form. So what we mean to see here is, so we will look at the network function. Okay, we will look at the network function. Okay, and based on the properties of the network function, we can classify that network function as an LC circuit or an RC circuit or an RL circuit. Okay, we'll first determine that. Okay, right? Okay, if once it satisfies any of the three conditions, okay, whether it is, if it is satisfying the LC circuit properties or RC properties or RL properties, then we can use the standard form of the circuit structure, the standard formulas, right, and do the synthesis in an easier manner. Okay, so that is the thing, right? Yeah, so for doing that, okay, so let us go for the standard approach approach for synthesis. Okay, yeah, so here, as I said, we look for the network function to satisfy certain conditions, certain properties, right? And decide the type of the network. Okay, so what network it is. Okay, yeah, so we have in standard form we have three types of networks that are possible. One is the RL networks, other is the RC networks, and the other is the LC networks, LC or RLC. Okay, it is a combination of you can take it anyway. Okay, so RL, RC, RLC. Okay, so these are the three possibilities that we can get, right, we can have. Okay, so based on the properties we can decide which type of function it is, and then we'll see. Okay, yeah, so firstly let us see what are the properties of these right, functions, LC function or RC function or RL function. What are the properties? Okay, then based on that how to do the synthesis, we will discuss one by one. Okay, yeah, so first let me take the LC functions. Okay, yeah, first first we will see the LC functions. Okay, so LC functions. Okay, so a network function will be called as an LC function if it satisfies two properties or two conditions. Okay, first thing is the network function, right? Okay, for an LC function, right, it will be the numerator and denominator will be a ratio of odd to even powers. Okay, odd to even or even to odd. That means P of s, if P of s is even, okay, then Q of s will be odd. Okay, if P of s is odd, Q of s will have only even powers of s. Okay, right? So what we are saying is the first condition is the first, and this condition is more than sufficient. Okay, the first condition is, right, okay, so the network function will be a ratio of, right, odd to even or even to odd. That means the numerator will have only odd terms, the denominator will have only even powers. Okay, right? Or if the numerator has only even powers, the denominator will have only odd powers. Okay, so if the network function is of this type, then that network function will be an LC function. Okay, it will be an LC function, simple. Okay, it will be an LC function, right? So you are going to get an LC circuit. Okay, an LC circuit, a regular combination of LC circuit. Okay, So that is the first condition. And second thing is, right, the second condition is the degree of numerator, minus the degree of denominator should be equal to 1, either plus or minus 1. Okay, right, plus or minus 1. So that means the numerator and denominator, okay, should be, right, should be the degree of the numerator and degree of denominator should be separated by only 1. Okay, that means if in the numerator, if this is s power 5, this should be s power 4 or s power 6. Okay, so the degrees of numerator and denominator should vary by only one quantity. Okay, these are the two conditions by which we can classify this as, right, a LC function. Okay, yeah, so the same thing, right? And one more very important, because of when this happens, right, when this kind of happens, so what happens is, if you look at the pole zero plot of the LC network function, if you draw the pole zero plot of the network function, okay, so we will find that all the poles, okay, and all the zeros, the poles and zeros of the network function will lie on the j omega axis itself. Okay, so all of them will be there on the j omega axis, right, and they will interlace with each other. Okay, so they will exist in pairs. Okay, because they are all imaginary, they are all lying on j omega axis. So, right, the poles and zeros, the roots of the polynomial, numerator and denominator polynomial, okay, they will be, right, they will be a ratio of odd to even or even to odd. So therefore, right, all the poles and zeros you will get will be having imaginary terms only, will all be complex and having real part as 0, so imaginary terms. Okay, and all of them will lie on the j omega axis, okay, in pairs. Okay, that is the thing. So all the poles and zeros of the network function will lie on j omega axis. Okay, and the second thing is they will interlace, poles and zeros will interlace about the origin. That means if there is one pole, then next to it will be a 0. Okay, pole 0, like this. Okay, so we will not have two zeros at one place or two poles at one place, right? They will be interlacing. Okay, pole 0, pole 0, like this. So all the poles and zeros will interlace on the j omega axis. Okay, so this is the third property, right, of the LC function. Okay, so LC function, right, when you can call a network function as LC function, simple. If it satisfies the first condition is, okay, it the numerator and denominator polynomial should be a polynomial of odd powers of s to even powers or even to odd. Okay, so numerator and denominator will not have all the terms. Okay, either only odd terms or only even terms will be present. Okay, and then the degree of numerator and the degree of denominator should vary or should be separated by a value of only 1. Okay, and the third condition is the poles and zeros, okay, or will all be lying on the j omega axis. That means they're all complex and imaginary. Okay, will all be purely imaginary. They will lie on the j omega axis and they will interlace with each other. That is, poles and zeros come in alternate. Okay, so one pole, one zero, one pole, one zero. No two poles or no two zeros will lie together. Okay, so that is the properties of this LC function. Okay, so when a network function satisfies these properties, it will be called as an LC function. Okay, so you check the network function, right? If it is satisfying these properties, then we can use the standard forms like Foster form or Coyer form to do the synthesis, because obviously you know the structure. What is the structure? You know. Okay, you will just use those techniques and find out the values, which we will discuss in the later sections. Okay, so this is about the properties of LC functions. Okay, right, now let us see the properties of RC functions. Okay, so RC function, right? Now what are the properties, or what is the check that we need to do for verifying whether it is a RC function or not? Okay, yeah. So two things. First thing is, so the degree of numerator and the degree of denominator should be same. Okay, right? The degree of numerator and the degree of denominator should be same. So first thing is, it should be same. Okay, So if it is not same, then we cannot call it as an RC function. Okay, so it should be same, right? And remember here, so in the case of LC, okay, in the case of LC functions, it doesn't matter whether you are taking an impedance function or an admittance function, the rules are same. Okay, that is whether it is given y of s or z of s, they are same. Okay, but in case of RC and RL functions, okay, so we are discussing the rules with respect to z of s. Okay, right? If the given network function is y of s, then you have to reverse them. That means whatever the properties that we are discussing for RC function in case of z of s will become the conditions for, right, RL function if the function given is y of s. Okay, if z of s is given, we are going to discuss the properties, right? They will be written as it is. Okay, but if the function given is y of s, admittance function, then whatever the properties we are going to discuss or the conditions that we are going to discuss for RC and RL, they become reverse. Okay, RC properties will become RLs, RLs will become RCs when the impedance function or when the network function given is an admittance function. Okay, so therefore we can say that, we can also write in most of the textbooks, right? So these are the properties of RC impedance functions or RL admittance functions. So if the network function that is given to you is an admittance, then it is representing an RL function. Okay, right? Right. Yeah. So considering it is an impedance function, let us say that, right, if it is an impedance function, then the degree of the numerator and the degree of denominator should be equal. Okay, so we cannot have a degree of numerator which is more than degree of denominator. Okay, so it can be less as well, it can be less, right? Degree of numerator can be less than the degree of denominator, but that doesn't happen rarely, right? Okay, but in most of the cases the degree of numerator should be equal to degree of denominator. That is a first condition. Second condition is, so once this satisfies, okay, then the next condition you need to check is z of 0 should be greater than z of infinity. That means if you take the impedance network function z of s, substitute s is equal to 0, you get z of 0. Substitute s is equal to infinity, you get z of infinity. Okay, you calculate z of infinity. So if the z of 0 is more than z of infinity, right, then it will be, right, a RC function. Very important one, because RL function, this property will satisfy. The only difference is this. Okay, yeah. So z of, you calculate z of 0 and z of infinity, right? If z of 0 is more than z of infinity, then you call that as an RC function. Okay, so in this case, right, if you draw the pole 0 plot, the third point, okay, so in this case all the poles will be real, okay, all the poles will be real and will lie on the negative real axis, all the poles and zeros will lie on the negative real axis, okay, negative real axis, right? Okay, why can't on positive real axis? Because I said, right, we are synthesizing only stable systems, only, right, systems which are, right, satisfying the stability condition. For stability condition, all poles and zeros must be on the left side of the j omega axis, so they will, right, therefore all the poles and zeros that you are going to get will be negative, will be lying on the negative real axis. They will all be real and negative. Okay, so they will all lie on the negative real axis. Okay, right, and and here, right, the quantity that is nearest to origin will be a pole. So a pole will be present near to origin, not at origin, but the one that is lying, the root of s which is lying close to origin is a pole, and the, right, a 0 will lie near to, right, infinity. Okay, so at infinity, right, right, we'll have a 0. Okay, so pole will be present, right, close to the origin, and 0 will be the last, so they will be interlacing, right? Poles and zeros always interlace. Okay, so one pole, one zero, one pole, one zero, like this. So near to origin we will have a pole, and near to infinity we will have a, right? If this is the infinity, they will have a 0. Okay, so these are the three properties that we will get for the RC functions. Okay, so these are the two conditions. These two conditions are enough. We don't need to check with the third. Okay, this is the property by which we get, okay, using this. Okay, yeah. So when the impedance function is given, right, then we have to check these three conditions, and if these three conditions are satisfied, we call that as an RC function. What are the three conditions? Degree of numerator should be equal to should be equal or less than the degree of denominator. Okay, second thing is z of 0 is greater than z of infinity. This is the condition you need to check. Okay, z of 0, when you substitute s equal to 0, we get z of 0. When I substitute s equal to infinity, we get z of infinity. So this should be greater than this. Okay, and the third point is all the poles will be negative, will be all lying on the negative real axis. Okay, and they will be interlacing with each other, and the poles, okay, there will be a pole near to origin and there will be a 0 near to infinity. Okay, so first will be here on this side, the first thing that comes is pole, and on this side the first thing that comes is in 0. Okay, so these are the three conditions that has to be satisfied for calling it as an RC function. Okay, if the right if the network function that is given is an admittance function, let's say if it is y of s that is given, okay, and if it satisfies all these three conditions, that is by taking, so first you have degree of numerator equal to or less than denominator, done, right? Then y of 0 is greater than y of infinity, okay, done, this is also satisfied. And the third, right, same thing, okay, all these things. In that case, if the given network function is y of s, then the circuit that is representing here is an RL admittance function, okay, right, RL function, RL circuit. Okay, so if for y of s, if we satisfy these conditions, the same conditions, then the resultant circuit will be an RL function, not an RC circuit. If impedance is given, it represents an RC circuit. If admittance is given, it is representing an RL circuit. Okay, yeah. So this is the second RC functions, the properties of the RC function and the condition when we can call this network function as an RC function. Okay, right. Now let us go to the third one. Third one is the RL functions. Okay, yeah. So again the same thing, right? RL functions. Okay, if you are synthesizing with the help of z of s. Okay, yeah, if the given quantity is y of s, then it represents an RC function. Okay, right? Yeah, same rules if it represents an RC function. Okay, yeah, what are the properties? Same thing, degree of numerator is equal to degree of denominator. Okay, equal to or less than, right? And there should not be difference not more than 1. Okay, so between the numerator and denominator degrees, there will be only a value of difference of 1, not more than that. Okay, yeah, so that is the first condition. Second condition is, okay, so here the change, z of 0 should be less than z of infinity. Okay, so there in the RC function and the RC case, we have z of 0 greater than z of infinity, but here the condition is z of 0 is less than z of infinity. Okay, if this condition is satisfied, you call this as an RL function. Okay, you call this as an RL function. If impedance, if admittance, okay, RC. All right, that we'll see. Okay, yeah. So third thing, because of this, what are the properties you are going to get? Again, here also the poles and zeros, okay, poles and zeros will lie on negative real axis, okay, negative real axis, right, like this. So all of them will be lying on negative real axis. Here the point we have to remember is the first right root of s, the first thing that we are going to get at origin will be a 0. Earlier it was pole, here it is a 0, and we will have, right, like this. So at infinity there will be a pole near to infinity, okay, right, and a 0 near to origin, okay. So right, at the first thing will be a 0, right, and at infinity there will be a pole. Okay, So these are the two things that we are going to get, right? And poles and zeros will be interlacing with each other. Okay, so that is also there, and all the poles and zeros will be right lying on the negative real axis. That means they are all real values and their magnitude is negative. Okay, so this is what we are going to get for an RL function. Okay, right, remember this thing. Okay, again, right, if it is z of s. Okay, if the network function given to is y of s. Okay, exactly same thing as I said. If the given thing is y of s, and if this condition satisfy, that is degree of numerator is equal to denominator, then y of 0 is less than y of infinity. Okay, and third, right, this poles and zeros lie on the negative real axis. In that case, the function or the circuit that you are representing is an RC circuit. Okay, it's called as an RC admittance circuit. Okay, so right, if the admittance function is given, if these three conditions are satisfied, it is representing an RC circuit. If it is impedance function, right, then if these three conditions are satisfied, okay, this is called as a right RL function. Okay, yeah. So right, look at the properties of the network function. Okay, you just in this is the standard approach. So first you look at the properties of the network function with and you compare them with LC, RC, RL. Okay, so if there is any match, then we can use the standard circuit approach that we have, right, using different forms and do the synthesis. Okay, if any of these three things doesn't match, let's say if the given network function doesn't match with either RC or RL or LC, then it is representing a arbitrary combination of RLC. Okay, it is not having a standard form. Okay, in such cases also we can synthesize. How, we will see later. Okay, so first we will discuss, okay, the synthesis of these LC, RL and RC. Okay, one by one we will take right, in each case we have four forms: Foster form 1, form 2, Coyer form 1, form 2. Okay, so in each case we will be discussing these four methods for realizing or for synthesizing the circuits, right? So after all discussing all these, then we will see the synthesis using any random or arbitrary circuit. Okay, yeah, so that is it for this lecture. So in the next lecture we will discuss the synthesis of LC functions. Okay, thank you.